Okay, thank you. So yeah, so thank you very much for the invitation, and I'm sorry I can't be there in person. But today I'll discuss this idea we've been working on, which is the production and detection of nuclear fragments at the future electron-ion collider. And I'll just give a brief introduction to the EIC. So in particular, the electron-ion collider, which is going to be implemented at Brookhaven National Laboratory to begin running in about a decade. And what will be done is an electron ring will be added to the existing RIC hadron or ion ring. And this will allow high energy electron, proton and electron nucleus collisions to be made and recorded. So in particular, the EIC will have a variable center of mass energy. So we'll have basically 5 to 18 GeV electrons colliding on protons of up to 275 GeV energy, and heavy or heavy ions of energy up to about 110 GeV per nucleon. We'll have a high luminosity at the EIC, something like 10 to the 33 to 10 to the 34 instantaneous luminosity. Both the electron beam and the proton beam or the light ion beam can be polarized, which will allow, for example, double spin asymmetry measurements. And there'll be a range of species from proton up to very heavy nuclei. And there'll be 2 possible detection areas. The first one, which is currently under design, is this, it will be at this IP6 location. And then there is a conceptual design for a second one at IP8, which I will discuss a little further. So the EIC will make very important contributions to our understanding of nucleon structure. In particular, we hope with the EIC to be able to study the full 3-dimensional momentum and spatial structure of the nucleon, including the spin structure through, for example, double spin asymmetry measurements. We hope to understand the origin of the nucleon and hadronic mass and how that mass is generated by the underlying internal photonic interactions. We hope to study the gluon density at the smallest momentum fractions and how the gluon density evolves towards low X. And then there's been a lot of work done on science beyond the 2018 NAS report on the EIC. And I'll discuss the specific idea we have to conduct some interesting work at the EIC. But I think in general, on a lot of the EIC science, there'll be a bunch of discussion, I think, in week 5 of this meeting. So I think stay tuned for that. Now, just to give briefly, without actually showing any specific timeline, just a little bit on the current status of the EIC. So basically, as I mentioned, there's a possibility for two interaction regions. The first EIC detector will be located at this IP6 place location. And basically, right now we have a fairly mature design for that interaction region, and we formed a collaboration, which is called the EPIC collaboration. And we're working towards a final or a close to final baseline design for this this first detector. And we hope the data taking can start in about a decade there. A second detector can be located here. And right now there's a conceptual design for that detector as well as the interaction region. And a working group has been formed to actually assess how this detector, the second interaction region and second detector, can complement and the physics being done at the first detector. So in whatever happens here with the construction, the data will begin a few years later than the first detector. And the detector design is still at a conceptual phase here. So today I'll discuss actually this idea we've had over the last year or so to actually look at nuclear fragments at this electron ion collider. So the motivating questions are really, can we use these high energy collisions, in particular with the heavy ion beams, to produce nuclear fragments, and can we detect those nuclear fragments, including exotic nuclei, such as undiscovered isotopes? And then if we can detect and identify these nuclei, can we, in addition, measure de-excitation gamma rays and coincidence? If we can do this, if we actually can do this, does that place some interesting or important requirements on the far forward detection area of the EIC? And then if we actually can do this production, detection, and identification of these nuclear fragments at the EIC, how would some of this work complement the work that's actually being currently done at dedicated rare isotope facilities? So just to give a brief qualitative schematic of how nuclear fragments will get produced at the EIC, we can think of we can look at this picture. So basically, we have initially a hard interaction between an incoming electron, which is, as I said, 5 to 18 GeV, and a high energy heavy ion. And after that, we have essentially a primary interaction followed by an intranuclear cascade. And this leaves us with an excited nucleus, which we call the residual nucleus or the excited intermediate nucleus. And this happens very quickly, instantaneously on the timescale of the detector. And this, again, instantaneously on the timescale of the detector, this excited nucleus will de-excite either through high energy fission or through evaporation. And after that, these evaporation products or these fission products will be in either in a ground state or in an excited state, and they can gamma de-excite. And lastly, they will, of course, radioactively decay. So where the EIC can potentially make some measurements is actually in this regime. So when you have these ground state isotopes following the fission or evaporation, they'll be highly boosted, and they can actually be detected in some of our detectors before they radioactively decay. And we can also perhaps measure these gamma de-excitation, these de-excitation gammas, which will also be Lorentz upshifted to energies that are much larger than the background photons present in the detector area. So this could potentially allow for clean detection and identification of these gamma rays, which can be used to study the level structure of the isotopes. So, so to give a few more specifics, which are still at this point rather qualitative or completely qualitative, what can the EIC actually contribute? So I think there's a few places. So in terms of reaction mechanism, so by studying the excitation energy distribution of the residual nucleus, this can be useful to improve the fast abrasion fission models and to understand the reaction mechanism for the production of these fragments. And then the EIC will have, as I'll show, the potential to actually simultaneously measure or detect 2 fission fragments. And they can do this, and we can do this without, since we don't have any target, we have 2 beams. These fission fragments will have no contribution from a target, no target modification of the fission kinematics. And this can be very useful for potentially for constraining or improving production models. For heavy nuclei that are produced, especially heavy neutron deficient nuclei isotopes in the range of Z of 89 to 94, there's some potential advantages over rare isotope beam facilities because these isotopes would have very short lifetimes, And the EIC, due to the high energies, would actually perhaps be able to detect them directly, these isotopes. Then, as I mentioned, in terms of nucleus structure, the ability to measure the de-excitation gammas as well as the produced isotopes in coincidence, it will be very useful. And then there's on the question of some of the models that we currently have, for example, for hadronic formation time in the nuclear medium. Basically the residual nucleus that is created in these collisions, the excitation energy distribution is actually sensitive to many of these formation time parameters. So the actually measurements of this can help constrain some of our hadronic formation time models. So how can we actually study this? So in particular, we're basically at the late stage where we do some simulations to study this. So we have this event generator which has been developed and which is actually continues to be developed, called Beagle. And Beagle basically is able to model the nuclear geometry plus the initial hard interaction, followed by protonic energy loss and the intranuclear cascade. And Beagle will actually lead, so when we run this Beagle simulation, it will provide us with this excited residual nucleus. And we can then take that excited residual nucleus and actually de-excite it using various de-excitation codes. And I'll show results from two of those. So one is FLUCA, and the other is ABLA-07. So basically FLUCA is a code that's of course used for a lot of dose estimates and is used extensively in heavy ion physics for various things, but is not really used, of course, for rare isotope type physics. ABLA-07 is actually used quite extensively in the rare isotope community, and it's the second part of the abrasion ablation code called ABLA-07. As I said, we run the Beagle events through both of these codes and compare the results. And then we also have a third code that we're starting to look at now. So the specific way we actually do the simulation is we simulate, say, an 18 GeV electron beam colliding with a 110 GeV per nucleon U-238 or lead-208 beam. And then we then study the excited residual nucleus that is created following the hard scattering and internuclear cascade. For this study we're doing, the only relevant quantities are the A and the Z of this residual nucleus, as well as its excitation energy. And when we also make this assumption, and the code doesn't have the capability right now to impart any angular momentum on this residual nucleus, so we assume it has zero angular momentum. And then so if we study this produced residual nucleus, what do we actually find? So we find that the production of the residual nucleus in Beagle actually manifests itself as a very simple abrasion model. So what I mean by that is the excitation energy of this residual nucleus actually depends linearly on the number of nucleons that are abraded from the beam. So if you look at the difference between the A of the residual nucleus and the A of the beam, the excitation energy scales linearly. And the spread of the excitation energy also has a simple dependence, as one would expect from an abrasion type model. And then basically the probability of abrading a given number of nucleons has this exponential type dependence. And lastly, the probability for a given number of abraded nucleons, so the probability of either abrading a proton or a neutron from the initial ion beam is just governed by simple combinatorics.
question. So, if you go, the energy you gain for removing each nucleon is like, if you go back to the plot where you see that, it's about 20 MeV, right? If you go back one more.
This one, yes.
Yeah. So what physics controls that the 20 MeV per nucleon excitation energy?
Right. So this is basically, yeah. So this is the outside. So as you're right. So the of course the nucleons are placed into sort of a mean field distribution, and then when they're actually removed, this excitation energy of the residual nucleus is governed by a couple things. So it's governed essentially by once the nucleon is removed, it's comparing the mass of that sort of the residual nucleus with the ground state mass of what that residual nucleus would be. So essentially, the model that's actually put into Beagle is actually basically has a few parts. So essentially, after the hard scattering, there's a hadronization there's a hadron formation time, and the hadrons that form inside the nucleus can basically remove additional nucleons, and those nucleons that are removed are basically sitting in a mean field with some Fermi distribution. So that's how they're modeled. So essentially, the residual nucleus, basically the energy of the residual nucleus at the end, basically just comes from the mass of the original nucleus, the beam nucleus, and then by also removing essentially the energy of the protons and neutrons that are knocked out during the hard scattering and the cascade, as well as including and then removing some of the recoil energy from the binding. So then this energy here is actually compared to basically the ground state energy for that given A and Z. And that's actually sensitive to some mass models that we have. So this number is a bit sensitive to the mass models, but the underlying physics comes from essentially, these equations here.
So I wonder, let's see, two things. First, does this depends on the energy, collision energy? That's the first part. The second part is like, if you have a PA collision or some hadronic collision, would this also apply this formula or not?
So yeah, okay, so for the first question, so I think at the EIC energies, this, at least the studies we've done so far, this dependence does not is very weakly dependent on the beam energy right now. And this distribution will depend some on the beam energy, because this is basically how many are removed, which depends on the cascade, how much of a cascade you have, which actually is sensitive a bit to the beam energy. But this actually dependence here on the excitation energy does not really depend on the beam energies that are used right now. And as for the PA collisions, so this actually, these models, so this model that's actually put in Beagle was actually evolved from DPM Jet. So DPM Jet actually did some similar studies as are shown in these references for PA type collisions, and yeah, so you actually do see similar type behavior in the PA models that were used before for DPM Jet.
Okay, the excitation energy will be similar.
So DPM Jet, the collision energies initially were lower. They were used more in some of the fixed target things, but yeah, so the square root of S was a little lower. But here, I think for the EIC, at least, and the range we've looked at, which has actually been square root of S from 20 up to 100, we haven't seen much dependence.
Okay, thank you. Go ahead.
Yeah, and yeah, I mean, I think the interesting thing that I wanted to point out here is that, you know, as I mentioned, really this is what actually is done in Beagle. It's this modeling of the intranuclear cascade plus basically having the nucleons originally with some geometric distribution and in some mean field with some Fermi momentum distribution. So the abrasion model that we see that was actually expected and that actually follows this simple linear dependence actually arises almost basically naturally from Beagle, which is so then what do we actually do with this? So on the left here, I show this residual nucleus. So this shows the number of protons in that residual nucleus. This shows the number of neutrons. And then of course, there's a third parameter, which isn't shown here, which is the excitation energy. Now you can see basically these different lines show the number of abraded nucleons compared to the U-238 beam. So as you move to the left here, you would actually have higher excitation energy. And then what's done, as I mentioned, we have these different codes and we de-excite this residual nucleus. And this shows what happens if we de-excite it with Fluka. This shows if we use this ABLA 07 code. And we use a little jargon here, which we have these two regions. One, which is we call the evaporation region, in which case you basically have this de-excitation. The de-excitation basically comes through by evaporating neutrons mostly and some light charged particles, which leaves us with one heavy nucleus in the ground state. Then we have this fission region, in which case we basically have we always have two medium mass fission isotopes produced. Okay, so if we actually compare these codes, we actually get a fairly good agreement. So this is shown for different Z values as a function of neutron number. We see some regions, for example, in this high Z, where ABLA is suggests a higher yield, higher production rates, and then here, for example, where Fluka suggests higher production rates. And this is, as I mentioned before, ABLA is a code that's been more tuned for isotope production. So it's something so this is more used as a way to perhaps test how in what regions the Fluka code is actually doing reasonably well here. But overall, I think the agreement is quite good. Okay, so the other approach we're taking, which we've just started, is we have this other code called LEASE, which is used at FRIB to do many studies and to do a lot of experimental design and analysis work. And this abrasion model that I showed from based on Beagle, which has this linear dependence of the excitation energy on the number of abraded nucleons and this exponential probability of abrading a number of nucleons, has also been implemented at least. And we actually see a somewhat, as can be seen in this green curve, a somewhat similar distribution or prediction from LEASE as with the other two codes. So I think overall we have some sense that we have sense that we can produce some of these isotopes at the EIC, of course with some large uncertainties right now. But and we'll want to do two things. So one, we want to kind of do additional studies with Beagle and try to tune some parameters and see how sensitive things are there. And we also want to run higher statistics and try and actually look for the expected event rates for very rare fragments. So, for example, what's shown here is if we focus in on this evaporation region, we see, for example, that this ABLA code suggests that we will actually produce this thorium-207 isotope. Which could be very interesting if it can be detected, because of course this is a new undiscovered isotope, and it's in this range where the EIC can potentially detect this very low, short-lived isotope, and that has an advantage over these rare isotope beam facilities. But to actually do some more to understand this better, we really need to actually try to simulate much higher statistics, because so far we've only simulated, say, the equivalent of 1 hour of beam time running. Okay, but if we assume for a minute that we will be able to produce some of these isotopes, The next question is really whether we can actually detect them at a collider type facility, a collider facility like the electron collider. So let me take a minute and actually explain how the interaction region of the EIC is laid out in very broad strokes. So basically,
5 minutes before the discussion.
Okay, I'll be about maybe 5-10 minutes. Yeah, okay, thank you. So yeah, so I think so we have about we have 3 regions right now at the EIC. There's a main detector region where we'll detect essentially our high Q² scattered electron, some of our and many of our other particles, say our CDIS hadrons, for example, or heavy flavor particles or jets. And then we have a far forward region over here, and what we measure there is essentially we measure very low the particles very close to the hadron beam. So those would be very useful for measuring, say, DVCS or DVMP protons, and also for measuring certain for vetoing certain incoherent processes. And then there's this far backwards region, which is used to tag very low Q² electrons, as well as to make luminosity measurements, high precision luminosity measurements. If we look at our main detector, the main detector basically will cover a region from theta of 2 degrees to 178 degrees. So this will be kind of from, as I mentioned, from sort of the high Q² electron and other things. And this is an example of how the detector, a concept of the detector will look as for IP6. It's been updated in the current EPIC collaboration is updating this baseline design. Now, as you can see, I'll make one comment, which is that you can see that acceptance is actually uniform here or symmetric here from eta -4 to +4. But of course, there's a lot more material on the right here than on the left, and that's just because the hadron beam has much higher energy, which comes in from the left, has much higher energy than the electron beam. Now, there's this far forward region, and in this far forward region, it's basically a magnetic spectrometer, and it has a lot of detection capabilities. I think for our purposes, it has 2 things. So one is it has what's called these Roman pot detectors, which are essentially 2 tracking layers, and they can measure local positions and angles. And then we have these gamma ray detectors, which we call gamma ray and neutron detectors, which we call the 0-degree calorimeter. And as I mentioned, we have a rather mature design for this IP6, where the first detector will go. And there's right now a conceptual design for IP8. Now, just the kinematics of the produced nuclear fragments are such that, interestingly, which we find in the simulation, is that the fragments will be very close to the beam direction and have basically very similar momentum to the beam. So, for example, in this evaporation region, these isotopes or these fragments will basically have exactly the same momentum per nucleon as the beam and have almost no angle with respect to the beam. In the fission region, we'll actually always produce 2 isotopes, and they'll both be Lorentz upshifted to actually quite small angles with respect to the beam. One will be at a slightly higher momentum per nucleon than the beam. One will be at a slightly lower momentum per nucleon. And then there's some light nuclei from the evaporation and Fermi breakup. So if we make a simple assumption just to start, that the momentum per nucleon of the outgoing fragment is the same as the momentum per nucleon of the incoming beam, then we can actually write this ratio of rigidity of the fragment to the beam which we call XL and we can say that that's actually proportional to the A over Z of the beam. So if we actually can somehow determine this XL, we can actually determine this A over Z of the fragment. So the way you actually do that is with this magnetic spectrometer, the position on your detector, your tracking detector, which we call this Roman pot detector, depends on your optics, this dispersion. And if you know this dispersion, which you do from your optics design, you can actually measure this X position and you can determine this XL, which allows you to determine A over Z. The trick, of course, or the one challenge is that you have to actually, the fragment actually has to get outside of the beam envelope. And what that means, what the reason for that is the beam has some spread in momentum and some spread in position and angle. And that actually requires you to actually build a beam exclusion region around which is the actual detector acceptance. So in IP6, which is the first design, which is, as I mentioned, more mature, there's actually basically a larger region of XL, or this rigidities are excluded, than in the conceptual design of IP8, which will have this secondary focus in our initial design. And that basically comes from the fact that this smaller beta function at the Roman pot. And you can see that basically this means that this exclusion region in IP6 in this high divergence setting, which is a high luminosity running setting, is about 6 centimeters, while here it's actually in the IP8, it can be very small with the second focus configuration. So what this actually means is that if you look at, if you actually take all the potential isotopes and you actually look at their X position at this detector, and you look at it at the IP6 optics, so the first detector, you basically get very few or almost none can be actually, or will actually get out of the beam envelope. But in this second detector, potentially, you could actually get a lot, basically almost a significant fraction, all but a few, are actually will get outside of your beam envelope and can actually be detected in your far forward detectors. And they'll be reasonably spread out from each other or separated from each other on the order of 10 to 100 microns. Now, to actually fully characterize the isotope, you also need to measure Z. And the way you can do that, which we've done some standalone simulations for, is you can actually make a small Cherenkov detector, which can be placed behind your tracking detectors. So, for example, if you had a thin quartz bar, which behind the Roman pot, then the number of Cherenkov photons produced would be proportional to Z squared. And this shows a simulation result where if we simulate a Z equals 90 isotope compared to a Z equals 91 isotope, basically the relative number of photons that are produced. As I mentioned before, in the fission region, the produced fragments will not actually have exactly the momentum as the beam, the momentum per nucleon as the ion beam. And you have to actually make a correction for that. But this can be done if both isotopes are actually measured simultaneously, and if you actually can measure both the angles and the positions at the tracking detector. Okay, so the last thing, so there's two more slides that I have, is basically what about the detection of the gamma rays? So in the far forward region, we'll basically have a detection capability to measure something like up to photons that are produced up to about 5 milliradians with respect to the incoming beam. And we can measure all the way down to 0, actually, because the way that the spectrometer works is that the beam bends away from its initial direction at the interaction point. So if we can actually measure those, we can actually measure very low energy gammas that are actually upshifted due to the high energy of the beam. So if we had something like a detector, which a ZDC, which has something like a 2% stochastic resolution, which is possible with, say, lysocrystals, then we would actually be able to measure these gamma rays to quite high precision. So, for example, if we had a 1 MeV gamma ray at 0 degrees, which is shown by this blue here, it would basically have a 240 MeV energy in the lab. And we would be able to measure something, we would basically be able to measure it to around 4% precision, which would correspond to about 40 keV resolution for 1 MeV gamma. So this can be very useful. This can be actually quite decent, provided we can also control the angular resolution. And this can actually really lead to good studies of their the structure, nuclear structure, in coincidence with the isotope measure detection. Yeah, so I think this is something we're looking into in more details right now, and we hope to really see that we can separate these de-excitation gammas from background photons produced in the primary interaction, and we hope to really see what constraints this actually places on the far forward detection region. So I think to just summarize, so I think our simulation studies suggest that the EIC has the potential to produce nuclear fragments using the various heavy ion beams. We believe that measuring these fragments can complement current and future work that's being done at dedicated rare isotope facilities. As you can see, some of the motivations I gave right now are very qualitative. So we're trying to work to try and figure out some more quantitative reasons of how the EIC can actually contribute to this science. And I think with the right combination of detectors, really these nuclei can be reconstructed using the proposed optics of the second detector, which has this with its secondary focusing. And then our studies also suggest that de-excitation gamma rays can be measured in coincidence with nuclear fragments to a high resolution. And as I showed in the beginning, the second detector is still very much a conceptual design, and there's a working group that's trying to optimize it. So there's some, given those timescales, there's a lot of there's time enough to actually think about what physics we actually want to do at the second detector, and whether this physics in particular, detecting these nuclear fragments, whether it can really be beneficial to complement rare isotope science, and whether it can actually place some good requirements on the detectors in the far forward region. So I'll just end by saying we have a small team working on this. It's basically, we work on this outside of our day jobs. So this is basically just, we do this, so it's very informal. And of course, if anyone's interested and willing to join, we'd be more than happy to have you. So thank you.
All questions? Yes.
So Brock, very, very nice, interesting stuff. So how many pions are produced in these?
Yeah, so in the central detector, you produce a lot of pions through the primary interaction, which of course, and the pi zeros, of course, decay into photons. What's interesting is not so many of those photons actually go very far forward, so into this ZDC detector. So we can separate them. We seem to be able to separate them from these de-excitation gammas.
Okay. I was actually more interested in the number of protons that are converted to neutrons and vice versa in this process. So if you, let's say you start up with uranium, so can you just count the number of neutrons and protons and they stay the same, or are they being converted?
So you mean in sort of this plot, with Beagle, for example?
Yeah. If I count the total number of outgoing, final protons and neutrons, are they equal to the uranium-238?
Yeah. So you get so let's see. So you get a few effects. So I think so you get some conversions in the thing. So that's not always the case. So for example, you can see that you get some events, say, above this line and to the right of this line. So that happens, I guess, when you actually, so there you have, say, more protons, right, than neutrons. So you actually get some conversions, right, inside there during the cascade. But the question is but you never get things you never get more, of course, you never go above zero here. So you will get an intermediate nucleus with an A greater than 238. But I haven't really checked if, for example, here, if you actually sum all the protons and neutrons that Beagle say exist in the final state, whether that sums to 238.
Thank you.
Okay, so the 1%.
I'm just curious, your initial dynamical process, do you consider the situation where your electron emit a photon that being absorbed by a subtly correlated neutron proton pair with 1.5 word, 1.4 word large relative momentum? How do you simulate those processes?
Sorry, I had a difficulty hearing you.
Okay, do you consider absorption of an electron by a subtly correlated neutron proton pair in the isocyclic time? Namely, subtly correlation. Do you consider subtly correlation in your initial?
No, not right now, not in the standard Beagle. So what we have, let me just show you. So what we've considered is there's a few effects in Beagle that are tunable. So we don't have this SRC. What we have is several effects. So we have this kind of this time constant for the hadron formation time. We have basically a different shadowing models, and we have basically different cascade parameters, like how long the cascade lasts for. So the shadowing basically takes into account how we handle the low X behavior. So whether we kind of roll the shadowing into like just a PDF effect, or whether we allow the photon to interact with multiple nucleons. So we have those effects, but we don't have any sort of SRC type effects implemented.
So have you considered, for example, now a rig also has Roman part, has the rig at calorimeter with actual very good energy resolution? Will you be able to say, okay, although we cannot discover maybe rare isotope, but for the existing ones, at least to prove the principles, it works, right? Because all the kinematics are the same as a rig.
Right. Yeah, I mean, so you can, yeah. So I mean, yeah. So the challenge that it seems to be when we looked at this for some current experiments is that a lot of the idea here is you have to design it beforehand to actually get this secondary focusing, to actually get the isotopes outside of the beam envelope.
Can you go to the beta star settings for these two? What beta star you can do? Mm-hmm. It's all driven by the beta star, right?
Right. So I mean, yeah, it's tuned by dispersion beta and then beta star. Yeah. So I mean, so in principle that's possible. So we could. So I mean, if it's a question, of course, what you tend to lose if you do it in some of this settings, you can tend to lose your luminosity and things. So it's possible maybe there could be some special runs or something where we could ask for it. But
yeah, a few years ago, there's a dedicated rig F run, which was using completely very different beta star just because the same reasons, right? It's a dedicated run.
Okay, thank you. Okay, I will follow up on that. Thank you. I'll see what's.
Can I move over there so I can be seen?
Oh, no, you can. Yeah.
I can go over there. Yeah, so the question I was wondering about is, could you elucidate a little bit the advantages more versus other means of calculating fission in a rare isotope facility? And the two things that come to mind are what are being done, for example, right now at the GSI. One is to run the fissionable beam, say uranium, through a lead target, and you excite the giant dipole resonance by electromagnetic excitation, which is causes an energy in there, which has a width which is something like 2 MeV, around 15 MeV, and then it decays. The other possibility is to hit it with a proton target. You can actually measure the scattered proton if you want. If you really want, they take a little bit more fissile nucleus, you might even be able to calculate the inelastic energy that's deposited by inelastic scattering. I don't know that they do that, but the first case seems to me that you make a nucleus which decays with relatively well-defined excitation energy. What is the advantage of doing it with a laser?
Right. So I think the potential advantages of the EIC are, so there's a few. So I think, at least some things that it can do. So one, since you don't have any target effects, I think you basically can, you won't have any effect on your kinematics due to any target contamination, for example. So you can measure the two fission products simultaneously, which actually allows a reconstruction of their initial, essentially, the initial nucleus. The third thing you get is basically the EIC is something of a survey experiment. So you can measure basically many of these isotopes in simultaneously in the same setting. You know, that the events, and you can build distributions very nicely.
Well, for example, at the GSI, they run this big dipole thing that with the rather small energy that's released in the fission, then they can detect both isotopes at the same time and measure their charges and their masses with silicon detectors.
Right. So I mean, yeah, I think, yeah, I mean, so the question there is, yeah, so I think it's a fair point, and I think we'll have to think about it more. I mean, so I think some things you get, as I mentioned, you don't have the target, which is useful. You also have the fact that you have this tuner, you maybe can study this as a function of sort of Q squared and X, which we haven't looked at yet, but could maybe affect these distributions a little bit. You know, these excitation energy distributions, but I think it's a fair point and something we have to think about more.
Okay, so I think it's a good, just a quick question. So you want to measure the gamma, but what do you handle? How do you handle this the pilot possible excitation, multiple excitation if you have high luminosity? Do you require some like low luminosity runs so you don't have multiple photons? The excitation photon goes to your ZDC, or?
So there's a few effects. So you have photons, of course, from a lot of different processes that are produced. Most don't go into your ZDC. Most go kind of at higher angles. There are a lot of them that are in the ZDC, with some exceptions, are from the de-excitation. You won't detect every de-excitation, and most will not go into their the ZDC each event. So it's something where you would detect some fraction and you would kind of build up a spectrum.
Thank you.